saw in the last video how the derivative of the function determines certain features of the original function. And we did so graphically. Well, now we're going to do so algebraically. But first, we're going to review a little bit. When f is increasing, recall that the first derivative is positive. When f is decreasing, the first derivative is negative. When f has a max or a min, that means the first derivative is 0. But it's vice versa if the first derivative changes from negative to positive or positive to negative. We also saw that the function has an inflection point when the first derivative has a max or a min, or when the second derivative has a 0. And we saw when it's concave up, the second derivative is positive, and when it's concave down, the second derivative is negative. So given a function such as this, to determine the intervals of where it is increasing and decreasing, the points of inflection, and then also the points where it's maximum or minimum, we must first find the first derivative. Well, here, finding the derivative, we see that it's x squared plus 2x minus 8. Factoring this out, we get x plus 4 times the quantity x minus 2. Well, this tells us that the derivative has zeros at the point negative 4 and also at the point 2. With the zeros of the derivative, we must now determine the sign of those intervals. So here we have three intervals: negative infinity to negative 4 to 2, and 2 to infinity. To determine the sign of the first derivative, we are going to choose a value between negative infinity and negative 4. So we can choose the value negative 5. So finding the f prime of negative 5, we get negative 1 times negative 7, which is equal to positive 7. So we know that the first derivative is positive between negative infinity and negative 4. Similarly, we're going to choose a value between negative 4 and 2 to determine the sign of this interval. So we can choose 0. So f prime of 0 is equal to 4 times negative 2, which is a negative 8. And so we know that between negative 4 and 2, the first derivative is negative. To determine the sign of the last interval, we choose a value between 2 and infinity. So we can choose the value, say, 3. So f prime of 3 is equal to 7 times 1, which is positive 7. So we know that the sign of the last interval is positive. So for the original function, when the derivative is positive, we know it is increasing. And when the derivative is negative, we have that the original function is decreasing. And when it's positive, the original function is increasing. And so at the zeros, for instance at negative 4, because the function is increasing and then it's decreasing, we know that it's going to be a maximum right here. And then at 2, because it's decreasing, so it's going down and it's coming back up, we have that it's a minimum at this point right there. So we can conclude that the function is increasing on the interval negative infinity to negative 4 and 2 to infinity. It is decreasing on the interval negative 4 to 2. It has a local maximum at negative 4 and has a local minimum at 2. To conclude more about the original function f, we are going to look at its second derivative. And to do that, we have to recall that the first derivative is x squared plus 2x minus 8. We then find that the second derivative is 2x plus 2, which is just 2 times the quantity x plus 1. And here we can see that the 0 occurs when x is equal to negative 1. Just like we did with the first derivative, we're going to find the sign of the intervals with the second derivative. So we choose a value between negative infinity and negative 1, say negative 2. So f of negative 2, f double prime of negative 2, is equal to 2 times negative 1, which is negative 2. So we find that the second derivative between negative infinity and negative 1 is negative. Now to determine the sign of the second derivative between negative 1 and positive infinity, we can choose a value, say 0. So f double prime of 0 is equal to 2 times 1, which is positive 2. And so we know that the second derivative is positive from negative 1 to positive infinity. With the signs of the second derivative, we can conclude that the original function is concave down between negative infinity and negative 1. It has an inflection point at x equals negative 1, and is concave up between negative 1 and positive infinity. So putting what we learned from the first derivative and the second derivative, we have that the original function is increasing on the interval negative infinity to negative 4 and 2 to infinity. We have it as decreasing on the interval negative 4 to 2. It has a local maximum at x equals negative 4, has a local minimum at x equals 2. It has an inflection point at x equals negative 1, and is concave down, negative infinity to negative 1, and concave up from negative infinity to positive infinity. So graphing this, it should look something like this. So here, as you can see, it's increasing all the way until negative 4, and then it's decreasing all the way to positive 2, and then increasing again, as we determined from the first derivative. But we also determined that it's concave down from negative infinity to negative 1, and then it's concave up from negative 1 to positive infinity.